Now in this problem we were asked to compare which function was growing faster, slower, or if they were growing at the same rate. So what that means is we need to set up a limit as x goes to infinity because we want to see what's happening as we continue in the positive x direction continuing on. And we are going to divide our two functions, and it doesn't matter which order you put them in, who goes to the top of the fraction, who goes to the bottom, but your conclusion is going to be specific to what ordering you chose. So for instance, if I choose to put f of x at the top, then I think of the limit of this fraction. Now the limit of a fraction can be considered as the limit of the top divided separately by the limit of the bottom. So this entire equation, its highest power is a cubic, so it's acting like the cubic function, which looks something like this. So this equation doesn't look exactly like this, but since the cubic is the highest power, as x goes to infinity, it's going to carry on this behavior of increasing without bound. So for that reason, we know that the limit of the top is infinity. Similarly, for e to the x, we have the equation for e to the x is this. So notice as x goes to infinity, the output value does increase to infinity as well. Now after you calculate a limit at infinity and you get infinity over infinity, this is an indication that we need to use L'Hopital's rule, in which we take the derivative of the top as a separate function and divide that by the derivative of the bottom. So the derivative of 10x cubed plus 2x would be 30x squared plus 2. Derivative of e to the x is e to the x. And as we consider this limit, again we have infinity over infinity, because this parabola goes to infinity as x goes to infinity, and e to the x is still going to infinity. So again, we need to use L'Hopital's rule. Sometimes you do have to apply this multiple times. Derivative at the top is now 60x divided by e to the x. 60x is just a straight line, a very steep positive slope, so that's still going to infinity as x goes to infinity, so we'd still get infinity over infinity. That means we need to use L'Hopital's rule again. Each time we use it, we just indicate it with this LR. Okay, and now 60 is a fixed number. Its limit as x goes to infinity. 60 is just the horizontal line at height 60. So as x goes to infinity, the outputs are staying consistently at 60. So this limit would be 60, but e to the x is still approaching infinity. So what we have to think about here is we've got a fraction where the top number is some fixed value and the denominator is increasing without bound. That overall is going to make an overall fraction that is tending towards 0. So we get the value of this limit would be 0 for that reasoning. Now once we get to the value of the limit is 0, that means that the function that was in the denominator is the one that's growing faster because it is bringing the entire limit to 0. So our conclusion would be that e to the x grows faster than our 10x cubed plus 2x. Now here we're asked if this is true, and we know this notation, x is equal to little o of x plus ln of x. This would be true if when we form this limit, what's inside the parentheses goes to the denominator. If when we form this limit and we evaluate it, in order for it to be true, it would have to equal 0. That's what the little o notation means. This would have to happen if we're going to say it's true. So we're going to evaluate this limit, and if we get any value other than 0, then this statement is false, but if we get 0 as a result, then it is true. So we know the limit as x goes to infinity of x is infinity, and in this case this one is as well because x goes to infinity as x goes to infinity, ln of x goes to infinity as x goes to infinity, so infinity plus infinity is still going to infinity. So this would indicate that we need to use L'Hopital's rule. So we've got the limit as x goes to infinity of 1 over the derivative of x is 1, the derivative of x plus ln of x is 1 plus 1 over x. And now as we think about these limits, we know that we could split the limit to the limit of the top times the limit of the bottom. And just by our limit laws, we could split it like this if we wanted to see it in each detail. Now both of these limits are just going to 1 because it's the limit of the constant function. And this limit here is actually going to 0 because we have 1 over an infinitely large number. The fraction gets infinitely small. So the value of the limit is 1, but that's not equal to 0, so we know our statement is false. Because to make this statement means when you form this limit, you should get 0. So if that doesn't occur, then we started with a false premise. This is not true. Now, as we look at this integral, we see that we have dx over x times the square root of 4 plus x squared. And one thing we notice is this 4 plus x squared could be rewritten as 2 squared is what 4 is, plus x squared. And the reason for this is now it's going to look a lot more familiar for one of our known integral formulas. So you would look at your integral formula sheet and see if this applies to any of them. And I think it's a pretty close appearance to our inverse hyperbolic cosecant. So this is from our list of known formulas. And notice in this case our x is taking the place of the u. 2 is taking the place of the a. And this is a perfect application of this integral formula. So we can just follow it along. We know that it will be negative 1 over a. Our a is 2. Inverse hyperbolic cosecant of the absolute value of x over 2 plus c. Now, as we think of this next integral, we see that u substitution won't work because if we let x squared plus 1 be the u, then du would need to be 2x dx, but we have an x squared term. So it seems like the power in the top is a little too high for that. So this would be a case where a useful trick will help us solve this problem. If we remember this, x squared could really be rewritten as x squared plus 1 minus 1, right? These are the same expressions. And the reason we're going to want to do that is if we rewrite this as the integral of x squared plus 1 minus 1 all over x squared plus 1 dx, then as we saw before, we can split the fraction. We could split it to this divided by this first, and then subtract this divided by this. Okay, let's split the fraction since we've got a single term on the denominator, and then we'll see how that helps things look out for us. But in this case, this integral, we can allow this fraction within the integral takes the place of 1 because it's something divided by itself. So the interior of this first integral simplifies to the integral of 1 dx minus the integral of 1 over x squared plus 1 dx. And for this one, since u substitution won't necessarily work here, we don't have the 2x term needed to counteract it, we would do well to look at our table of integral formulas in order to try to evaluate this. So if you haven't already, take a minute to pause this video and look at the formula sheet and identify what integral formula we're going to use here, and then unpause when you're ready to check your work. So in this case, our formula for inverse tangent is a direct application here, because although the a squared comes first here in the formula, order of addition doesn't matter, so we could have rewritten this as 1 plus x squared if we want to, just to see how that works. So then we know the integral of 1 is x. Normally I write a plus c, but I'm just going to wait to write my plus c till the end. minus this would be 1 over 1, a is 1 here, inverse tangent of x over 1 plus c. Now all this can be simplified. Okay. Now our next integral, again, u substitution wouldn't work here because there's nothing that could take the place of the du. If we let u be x minus the square root of x, there's no du term occurring. But if you look at the denominator, there is a common term to both sides of the minus side, and that common factor is the square root of x. So whenever your denominator has a common factor and you don't know how else to get started with the integral, you might try factoring out the common factor. It's not going to work every time, but it's worth a shot. So here, if we factor out a square root of x out of x would leave you with square root of x, because square root of x squared is x. And when you factor out the square root of x from itself, you're left with 1. And now is the time that we'll be able to use our u substitution. So let's let u be our more complicated term, the square root of x minus 1, because we know as we differentiate this constant minus 1 will disappear. So then du is 1/2 x to the negative 1/2 dx. And notice that's exactly what we have here. This x in the denominator is the exact same thing as x to the negative 1/2 dx. That's just expressed in a different way. So you can either write in the denominator as the square root, or you can write in the numerator and include the negative square root, because the negative is what brings it to the denominator. So we see we have this almost perfectly, except we don't have the 1/2, so we're going to have our 2 du. And now we can just input these here. And our integral becomes the integral of 2 du all over u by known integral formula. We know that's ln of absolute value of u plus c, substituting for u. And our guidance for why we at least tried this is, remember, not at every integration technique you try will work, but if you try enough things for the same problem, you'll probably find the right solution. So here, what helped me realize I could factor out the square root as a proper solution is I saw that there was something common to both sides of the expression in the denominator. If I factor that out, that generates something that I could use as my du in this particular case. Now, as we look to integrate this next expression, we notice that the power of the numerator is higher than the power of the denominator. So this tells us that we need to work through synthetic division to simplify this fraction. So from synthetic division, we are going to put what's in the numerator inside our box. And we think, what times 2x would give us a 4x squared? That would be a positive 2x. Multiply this through each part of our 2x plus 3, and we get 4x squared plus 6x. Now, since this is long division, we're actually subtracting this entire expression. So when we distribute the subtraction to both of our positive terms, that actually brings this a negative and this a negative. 4x squareds cancel, and we get a negative 6x minus 7. In order to get 6x from 2x, or negative 6x, we would need to multiply everything by a negative 3. That gives us the negative 6x minus 9. Now all of this was getting subtracted, so we have to think about distributing this. Minus a negative becomes positive for both of these. The 6x's cancel, and we're left with 2. Now at this point, our 2 is lower in exponents or degree than what we started with. We started with an x term. So that's how we know it's our stopping point. So the equation 4x squared minus 7 divided by 2x plus 3 is equal to 2x plus 3 plus 2 over 2x plus 3 is our remainder term. Oh, but I wrote this wrong. This was a minus 3, so this should be a minus 3. So yeah, 2x minus 3 with the remainder of 2 over 2x plus 3. So this replaces our integrand. And in this case, we could integrate this, and particularly this portion, as we integrate 2 over 2x plus 3, you could use U substitution, or you could recognize this as one of our f prime over f integrals, which the result of that is just ln of the original function in the denominator, and that's exactly what we could do to apply here. We know whenever we integrate 2 divided by 2x plus 3, that's actually just going to be natural log of the absolute value of 2x plus 3. So either by U substitution or recognizing this nice integral formula applies, we can integrate term by term. And we're going to get x squared minus 3x plus 2 times the natural log, or no, sorry, just natural log of 2x plus 3. Since this was a definite integral, this is from 3 to negative 1. We're now going to substitute in the values for 3 in every x here, and then subtract that from substituting the value of negative 1. So this would be now the natural log of 1 is equal to 0. You can check that in your calculator if you like. So this will simplify to natural log of 9 minus 1 and 3 come together to be 4. And notice here I very carefully offset the second term in parentheses to make sure the negative gets distributed properly. So we added these together first before we distributed the negative, and that would be our answer. And if asked to round this to so many decimal places, you could of course type it into your calculator, get the decimal approximation, and round. Now looking at this integral, we notice that we've got an x in the denominator, which we should keep in mind could be rewritten if we wanted to as this. We know we could separate the bottom of the fraction if it's just written through multiplication. And the reason this might be of use to us is notice what we're squaring on the inside is ln of x. So this divided by x term out front looks a lot like the derivative of ln of x. So maybe we could find a way for a U substitution to work. But as we look at this more, we notice that this interior is 1 squared minus 2 ln of x all squared. Dx. Now I recommend you take a moment to look at our list of integrals from our formula sheet, pause the video, and identify what formula applies here, and then when you're ready, unpause to check your work. Now first, since we are squaring a somewhat complicated expression, this isn't just x squared, I'm going to first use U substitution. To simplify, if we let u be 2 ln of x, du is just 2 over x dx, which we have exactly. That's perfect. So this simplifies to the integral of 1 over the square root of 1 minus u du. And now written in this way, we can identify this from our integral formula sheet. And we see this fits inverse sine because we've got the constant squared minus some variable squared. So using this integral formula, u divided by 1 is just u. Substituting for what u is,